I will talk here about the problem of finding the optimal maintenance schedule for hydropower plants. To briefly summarize the problem, we must understand that a hydraulic production system is not composed of a single block. It's actually several reservoirs which work together with turbines, and each turbine produces energy and works as a production unit. In addition, a hydropower plant is generally considered to be connected to other sources of production, for instance thermal sources. The management problem of such a system is therefore to determine for each time step on the horizon what each unit will have to produce to minimize costs while satisfying demand. This is a classic unit commitment problem, which we call W. If we add maintenance variables to this problem, we are adding constraints on the production unit. For example, if we decide to carry out maintenance on unit 3 at time step 5, this unit will not be able to produce at that time. We then have a parameterized GC problem, which is to obtain the minimum on Z of our function W, where Z is a maintenance planning. This problem is non-convex and very large, because typically in real life you will have systems that are huge and have many variables, and since we want to obtain our planning fast, we cannot solve it directly. Our resolution approach was therefore a two-step process. First, we decided to consider a convex surrogate for our function W, denoted bar W. We can show that bar W and W have the same Lagrangian, and therefore the same minimum. We also have that bar W is between W and its Lagrangian function θz, which is also parameterized. That allows us to operate our minimization on a convex function, which is much easier to do. However, the problem is still very large, so we still have to find a smart way to minimize it quickly. In order to do that, we decided to use a bundle method. The principle of a bundle method is to iteratively construct an estimate of our function using a cutting planes model. At each iteration, we get an estimation of our function and its subgradient, which allows us to enrich our cutting planes model with a new tangent plane. We then gradually converge by tightening the upper and lower bounds. In our case, we actually needed to use two nested bundle methods. Indeed, we needed a first bundle method on θz, the Lagrangian function. Indeed, this allows us to get an estimation at point z of our function bar w and a subgradient of that function at the same point. Those two results then allowed us to compute a second bundle method on bar w, which allowed us to get the optimal maintenance schedule z star, which is the final goal of our project. Future work on this project could include testing our algorithm on a bigger instance than the one we used for the first test, and also to compare its efficiency to other existing algorithms on that problem. It could also be very interesting to use SMS++ tools from the Plan for Rest project to implement our method.